In the next section, we're going to look at how integrals can be used to solve differential equations. One of the early accomplishments of calculus was predicting the future position of a planet from its present position, which is called the initial condition, and its velocity, the rate of change. Today, this is just one of a number of occasions on which we deduce everything we need to know about a function from one of its known values and its rate of change. And remember, rates of change are actually derivatives. So what we're going to be looking at is when we know an initial value and we have an equation for the derivative of a function. First up, consider the derivatives of y equals 4x squared plus 1 and y equals 4x squared plus 5. Since the constant disappears, the derivatives turn out to be the same. And we know if we want to reverse the process and get the original function back, we use plus c to remind us that there may have been a constant. If we have some initial information, we can actually solve for that particular constant, which is what we're going to be doing here. So any equation that contains a derivative is called a differential equation, or you'll hear people call them diffie-qs. If you're given an initial condition, we can solve for c, and then this is called an initial value problem, or IVP. To solve differential equations by the process known as separation of variables, you separate the two variables on opposite sides of the equal sign and integrate. As always, we'll take a look at some examples. These two examples are not in your textbook. First up, in example A, we're given that, and notice we have an equation that has a derivative in it, dy dx equals 8x. And we know that for the function y, when you substitute 1 for x, you're going to get an output of 3. We're trying to find the original equation y. So this isn't terribly difficult to do. This is a fairly simple example to start with, just to show you the process involved. You're going to take the derivative equation and separate the variables, meaning I want everything that has a y on the left and everything that has an x on the right, including this little dx. So I'm going to begin by multiplying both sides by dx. Now my equation says dy equals 8x dx. And this should remind you of things that we would see when we were doing use substitution. But in this case, what we're going to do is we're now going to, since I know dy and I want to solve for the equation y, I want to integrate my derivative so they cancel each other out. And what you do on one side, you will do on the other. So the integral of dy is just y plus c. And the integral of 8x is going to be 8. We're going to make the x squared and divide by 2. And there would be a constant there as well. I can simplify the first term, and I get 4x squared plus c. Now, the situation with the constants is we don't actually need to put a constant on both the left and the right, because ultimately what's going to happen, if I number my constants, I'd want to move the constant from the left over to the right to get my equation solved for y. And so I end up with a constant term that's made up of constant 2 take away constant 1. But if you subtract two constants, it's still a constant. What we do instead is we don't put a constant on both sides when we perform the integration step. Usually we opt to put it only on the right side where the x's are, because you're going to get to exactly the same answer, which is that the equation y is equal to 4x squared plus a constant. Now I can take my initial value, which is at 1. I know the output is 3. I can substitute those into this equation to find c. And clearly, c would need to be -1. I was able to determine the whole equation, including the constant. And notice this should make sense. If I take the derivative of this, dy dx, use the power rule, I do get 8x with my constant disappearing, and notice that's what we started with. So to solve a differential equation, one of the strategies is to do this separation of variables. Now in example B, you're going to notice that here we've got the prime notation for a derivative. There are two different notations, and it has to do with the fact that there were actually two people who discovered the bulk of calculus at about the same time, which was Isaac Newton and Gottfried Leibniz. And Newton's notation was the prime, I believe. Leibniz used this dy dx. Well, for separation of variables, it is helpful to use the dy dx notation. So the first thing I'm going to do here is get rid of my prime notation, keep everything else the same. And notice this time I don't have any initial condition, which means all I'll be able to do is get the y equation plus some constant, and that will be my answer. When you have a fraction equal to a fraction, the easiest thing to do is to go ahead and cross multiply, because you can see what's going to happen is on one side I'm going to get y dy equals, and then when I multiply along the other diagonal, I get 2x dx. So my separation of variables has been achieved just by cross multiplying. That won't always be the case, but if you can cross multiply, it's usually a good place to start. Now I'm going to integrate both sides. Y dy will become y squared over 2. And again, I'm not going to bother putting a constant on the left and the right. I'll save it for the right side. And the integral of 2x dx is going to be 2 with an x squared over 2. Here goes my plus c. Simplifying that equation, we have y squared over 2 equals, I'm going to cancel both my 2's, and I have x squared plus c. To finish solving for y, since y squared is being divided by 2, I would do the opposite to both sides and multiply by 2. We get y squared equals, and that kind of looks like a squared, so I'm going to rewrite that. I'm multiplying by 2. 2 times x squared is 2x squared. And watch what happens here. Again, if we do 2 times a constant, it's still a constant. So I don't need to bother writing that 2 there, because this constant c just absorbs that. And then the last step in solving for y would be to take the square root. And again, the constant can kind of just hang out at the end. Since I don't have any initial condition information, that's as far as I can go with this one. So solving a differential equation means you're taking an equation that has a derivative in it and going back and determining the original function. This is example, it's not actually both example 1 and 2, but examples 1 and 2 in your textbook are related. One of the most famous situations where differential equations come to play is in Newton's law of cooling, which is what this equation is an example of. So we're going to let y of t denote the temperature in degrees Fahrenheit of a cup of coffee at time t being measured in minutes. Room temperature is 70 degrees Fahrenheit. The coffee starts at a temperature of 190 degrees Fahrenheit. The coffee's temperature is described by the initial value problem, y prime equals negative 0.1 y minus 70. And the starting condition is y at time 0 is 190. So right here, this is a special case of Newton's law of cooling. And we're asked to find, first of all, how hot is the coffee after 10 minutes? The first couple of differential equations we looked at were fairly simple to muddle through. Depending on what your derivative looks like, though, it can become a little bit more complicated, as you're going to see in this particular example. We begin the same way by taking the equation of the derivative. I'm going to swap in the alternate notation for the derivative, but instead of dy dx, I'm going to pay attention to the fact that my x variable is now t. So I will put dy dt equals negative 0.1 y minus 70. Now it's easy enough to get the t over onto the right side simply by multiplying by the dt. So we're left with dy equals negative 0.1 times y minus 70 dt. These things are all being multiplied, so I can move the y term back over to the left, which is where I want it, simply by dividing both sides by that term. And I now have dy over y minus 70 equals negative 0.1 dt. Now that my variables are separated, I can go ahead and integrate. On the left, to do this integral here, we're going to want to do a u substitution, where u is my denominator of this fraction. Du just becomes dy. On the right, I don't need to do anything special there. I have the integral of 1 over u du will equal negative 0.1 t, and I'll opt to put my constant on the right. The integral of 1 over u is the natural log of the absolute value of u. And remember, u was y minus 70. We're trying to find an equation in terms of y. So this is where this one gets a little bit icky, because the y is trapped inside of this natural log. So one of the techniques you should have learned previously, exponentiation, where you exponentiate both sides, meaning take what's on the left and make it an exponent. And because we have natural log, we would want our base for that exponent to be e. So we're now going to have e to the natural log of the absolute value of y minus 70 when we exponentiate the left. We have to do the same thing on the right, and we must use the same base, and now take everything that's there and make that an exponent. Now what that does is the exponential function is the inverse of the natural log. So these end up wiping each other out, and we are literally just left with the absolute value of y minus 70 equals all of this stuff on the right. And then you need to remember how to handle absolute value equations. When you have an absolute value equation, there's actually two equations contained in there, where I have y minus 70 equals the positive e negative 0.1 t plus c. But the stuff inside y minus 70 could also turn out to be the negative e to the negative 0.1 t plus c. Now, normally we branch the two equations separately like that, but I can write it as just one equation and put the plus or minus in front of that right-hand side. So my equation becomes y minus 70 equals plus or minus e to the negative 0.1 t plus c. To finish solving for y, I am able to move the 70 over to the other side, and I have y equals the positive or negative e to the negative 0.1 t plus c plus 70. Now there's some additional cleanup that can actually happen with this equation to simplify our life a bit. And you should remember the exponent rule, that if you are multiplying things with the same bases, that you're allowed to add the exponents. Well, similarly, if I have an exponent that is a sum of two parts, I can work this rule in reverse and split it up into a product of two terms. So I'm going to choose to do that in this particular case. I will have this plus or minus in front. I will split this into these two terms. Now, why would I do that? Well, the reason for that is this e raised to the c power is a number raised to a number. So it itself is just a constant. And putting on a plus or minus also is still just a constant. So I'm going to turn all of this just into a single capital C of e to the negative 0.1 t plus 70. And if I did not have an initial condition, this would be my solved differential equation. However, we do have an initial condition that was given to us. Way back up here, we were told that at time 0, the coffee is 190 degrees Fahrenheit. I'm going to use that information to solve for my constant. So 190 is equal to C times e to the negative 0.1 power times time is 0 plus 70. This makes me happy because 0 times anything is 0, and e to the 0 power is just going to equal 1. So I'm really left with a very simple equation of 1 times c, which is c, plus 70. So therefore, my c is going to have a value of 120. So my completely solved differential equation with this starting condition would be 120 times e to the negative 0.1 t plus 70. I can now use that equation to answer the original question, how hot is the coffee after 10 minutes? All I'm going to do is substitute t equals 10 into my differential equation. 10 times negative 1/10 is just going to be negative 1. And if you type this into a calculator, you will get the decimal approximation 114.146 degrees Fahrenheit. So after 10 minutes, that would be the temperature of the coffee. And the last thing that we're asked about is how hot is the coffee at any time t? So at any time t, you can obviously just substitute whatever t value you want into this equation, and it will give you that information. Or you can opt to solve this equation for t, but again, you have to remember some of your algebra skills. You would begin solving for t by moving the 70 back over to the left. You would then want to divide off that constant of 120 on both sides. And once you have the exponential expression isolated, because that t is the exponent, what we're going to do is kind of the opposite of the exponentiation we did earlier. We're going to want to take the inverse operation for exponential functions, which is the natural log, and do that on both sides. So on the left, that stays pretty icky looking, y minus 70 over 120. On the right, the natural log is the inverse for e. So again, these just cancel each other out. We're left with negative 0.1 t. And the final step to get t alone is just to perform division. So that's just a little bit of an algebraic review for you. Again, some skills you may not have touched in a while. Another application of integrals, another thing that we can use them for, is to solve differential equations like this one.